my videos. Hey, welcome back. We are going to continue our discussion on work. And in an earlier video, you might remember we defined work as our force vector dotted with our little piece of our displacement vector, dr. Now the problem is dr is really tough to compute sometimes. For example, if we're going along a curve here, r of t, it's really hard to integrate our displacement because the displacement is constantly changing right here. So instead what we said is we're going to be looking at another way we can look at it. We're only going to be looking at the piece of the arc that we're going to be on. Now if we're on the arc at some point P right here, we are heading into the direction of t, our unit tangent vector. And remember, we have some force being applied to that our position, and what we want to find out is, well, what is the force of our force, what is the work being done of our force vector on our direction, t. And that's what this gives us for, this f dot t. Remember, this is the part of the force that is in, this is part of the force that is in the direction, that is in the direction of t. And this was a projection for us. This is that projection of f onto t, right there. And that gave us this little ds. Now, if you forgot where this came from, in my previous video, we kind of showed where it all came from. We got our projection, the f dot t, and this becomes s. That's that little piece of that arc length. Now again, arc length was very difficult to solve for because remember, arc length is going to be in terms of multiple variables, and that gets complicated. So we converted this to a parametric. We convert ds to a parametric, and we get r prime of t dt. You can see another video where we did that. So let's take a look at an example. We want to set up a work integral. There's our vector field, and there's our little piece of our displacement, and it is a line integral. Remember, a line integral just says, hey, look, we're integrating a line in 3 space, and we're going to see what's going to happen to it. Where our force is given to us by this vector. There's our force vector. In other words, this is the force that's exerted on our path. And the path is given as a vector, or as a parametric, I guess. So we can write it. So our path is given to us as a vector in terms of t. And what's nice about being in terms of t is now we can get rid of all these little variables, these x, y's, and z's. Remember, because ds, or to integrate arc length, is really kind of difficult with multiple variables, but if I can get it in terms of one variable t, it will make it a little bit easier for us. And that's exactly what we're going to do. So the first thing is we have to find our vector field along the curve. Well, what is that telling us is that we have to convert our vector field, our force, into in terms of t, using our path. Well, we know that our x of t, oops, let me give you all that, I don't know what that is. We know that our x of t is just t, our y is just t squared, and z is t cubed. I can plug each of those into our force vector, our force equation. So our force in terms of t would be the following. This becomes 8 t squared, because remember x is t, times y, which is t squared, times z, which is t cubed, comma 5z, which is t cubed, comma negative 4x, which is t, times y, which is t squared. And I can simplify this, and that's just going to become 8t to the 7th, 5t cubed, and negative 4t cubed. Our next step is to get the derivative of our path, of our parametrization. So this is our path. Take the derivative of that, and that's not bad. The derivative of t is just 1. Remember, we're taking the derivative with respect to t here. So this is going to become 1 2t, and 3t squared. So when we're solving this now, remember we're going to multiply our force times r prime of t, but this is a dot product. I want to get a scalar, so we're going to be using a dot product here. So my next step is just to take the dot product of our vector force field and r prime of t. And if we do that, we would get 8t to the 7th plus, what's that, 10t to the 4th minus 12t to the 5th. And what we wound up with here, remember, this is my force times my change in position here. And now I'm just going to plug that into my integral to get work. From our t values go from 0 to 1, 0 to 1, 8t to the 7th plus 10, that's a t, not a z, t to the 4th minus 12t to the 5th dt. And I can integrate this. This is not that bad to do. We're going to get t to the 8th plus 2t to the 5th minus 2t to the 6th from 0 to 1, and we would get 2 minus 2, whoops, sorry, not 2, excuse me, 3 minus 2, which is 1. We don't have to worry about the 0 because it all just goes to 0. And that would be our force on this right here. Remember, what this does is it evaluates the force of a field on a path of an object, and this would be like our net amount of work there. If you look down here, this is just kind of more of an explanation. You can take a look at the notes right there, and we kind of explain it up in the video. Remember, we're looking at our gradient, not our gradient, but our projection, and no matter where, it's just the same little formula right there. And the force is always going in the same direction. So let's look at another example. We want to find the work done by the following force, negative 1/2 xi minus 1/2 yj plus 1/4 k on a particle as it moves, along the path given by r of t. Now if we notice, what can we say about our path? Well, this should be easy for us by now. This is our spiral. So it's our helix, right? So it's our spiral, so it's kind of like this. We should be really used to these by now. We've seen them quite a bit throughout the year. They should be in your DNA. Ha ha ha. And we do want to control our time. How much time are we on there? So we're going to go ahead and get our bounds. So to get the bounds, we're going to look at time again. Now, remember, if this path goes along this path, we're starting at the point 1, 0, 0, and ending at the point negative 1, 0, 3 pi. So this path has to intersect these points, which means that at the same t value, every component of our path has to be at this point right here. So if I want to solve for t, I only have to pick one of them. I'll pick the last one, z of t. So here we're saying z of t. Well, what is z of t equal to at the beginning? 0. Well, what is t equal to? Well, we're saying t is 0. At the end, z of t again, I'm going to use z of t again, but this time we're saying t equals 3 pi. So we're going from 0 to 3 pi. That's terrible looking. That should be z of t, because that's what we're using here. Now we're going to go ahead and write our force equation to get our force equation here. To do that, well, I want my force to be a function of t, x of t, y of t, z of t. And it's really not that hard to get. I'm going to write this as a vector because I'm told x is cosine, y is sine, z is t. So I can just go up here. This becomes negative 1/2 x, which is cosine of t. Y, the next one is negative 1/2 y, well, we're told y is sine of t, comma, and that 1/4, that's my z component, but it's not in terms of t, so I can just leave that as just 1/4. And there we go. There's our fourth vector. So there's our vector, our force equation as a parametric now. And the next thing we need, of course, is r prime of t. We have to take the derivative. That's not hard to do. Negative sine of t, cosine of t. Because remember, I'm getting it from r up here, and then comma 1. Our equation, remember, to get work, is the line integral of our vector force times r prime of t dt. So now we're going to do that dot product. So I'm going to take f dot r prime. I'm just going to take that dot product. Multiplying together, we get negative 1/2. This becomes cosine times sine. Cosine t sine of t. And that actually becomes a plus because the two minuses cancel each other out. Minus, and this becomes 1/2 sine t cosine t. Oh, that's nice. They're going to kind of cancel out each other here. Plus, and this is just 1/4. And yep, oh, look how nice this is. Those cancel, I'm just left with 1/4. And now we're going to evaluate our line integral. So I'm going to get my work equation. Remember my work equation. Take my dot product, which is just 1/4 dt, and remember my domain is going to go from 0 to 3 pi over here. And this one's not that bad to do. We get 1/4 t from 0 to 3 pi, which is just 3 pi over 4. And there is our working element. Spirals are nice. We like them. All right, come back for the next video. We'll take a look at a couple more examples. I'll see you then. Bye-bye.